Volcanoes. As described online, a volcano is an opening in the Earth's crust that allows magma, hot ash, and gases to escape. Showcased in that explosion, volcanoes are incredibly large, destructive, and release tons of molten hot fluid called primarily lava or magma. Welcome to our project, and today we'll be trying to understand these processes. First of all, let's go over a quick history of volcanoes. In ancient times, early civilizations observed volcanic activity and often associated eruptions with the actions of supernatural forces. For instance, the ancient Romans believed Mount Vesuvius was a forge of Vulcan, the god of fire. During the 16th through the 17th century, as natural philosophy developed, scholars began to question the mystical origins of volcanoes. They noticed patterns such as a link between eruptions and earthquakes. Early theorists such as René Descartes, hypothesized that volcanic activity was driven by subterranean fires fueled by combustible materials. In the 18th century, chemists like Joseph Priestley and Antoine Lavoisier explored gases' role in natural processes. The discovery of gases such as carbon dioxide and sulfur dioxide in volcanic emissions highlighted their critical role in eruptions. Giovanni Arduino classified volcanic rocks and observed that different types of eruptions produce distinct materials. He introduced the idea that eruptions were linked to chemical reactions in the Earth's crust. By the 19th century, scientists like Humphrey Davy and Michael Faraday identified that minerals in volcanic rocks were formed by crystallization from molten magma. Davy's work on gases revealed the role of sulfur and chlorine in volcanic emissions, advancing the chemical understanding of eruptions.
After going through some old history, let's review some more modern approaches. Development of instruments like gas chromatographs allowed detailed analysis of volcanic emissions. Researchers discovered that gases such as water vapor, carbon dioxide, and sulfur dioxide dissolved in magma drive eruptions with pressure release during magma ascent, causing explosive outbursts. Theory of plate tectonics revolutionized the understanding of volcanic activity. Scientists linked eruptions to mantle convection, subduction zones, and mid-ocean ridges. Detailed studies of eruptions like Krakatoa, 1883, and Mount St. Helens, 1980, highlighted the chemistry of pyroclastic flows, ash clouds, and volcanic gases. Today, satellite imagery, spectrometry, and remote sensing allow continuous monitoring of volcanic emissions. Instruments detect gas compositions including SO2, CO2, and H2S, providing early warnings of potential eruptions. Isotopic analysis of volcanic gases offers insights into the Earth's mantle composition and magma sources. Studies of ash and lava provide a deeper understanding of mineral crystallization and the cooling rates of molten rock. The role of volcanic aerosols in climate regulation, for example, Mount Pinatubo's cooling effect in 1991 underscores the importance of chemical analysis in understanding eruptions' global effects. Let's finally move on to its ties to chemistry.
The first process of volcanic eruptions would be the magma formation. Chemically, magma is the molten rock beneath the Earth's surface, mostly composed of silicate minerals, which are compounds that contain silicon, oxygen, and at least one metal, with varying amounts of gases like water vapor, carbon dioxide, and sulfur dioxide. They are formed through subduction zones. At convergent plate boundaries, where two or more tectonic plates move towards each other, subducted ocean crust, which are ocean crusts that have gone under another tectonic plate, melts, introducing water and volatile compounds into the mantle. This reduces the melting point of surrounding rock, generating magma. There are different types of magma, mainly basaltic and rhyolitic. Basaltic magma is rich in iron and magnesium, and low in silica, leading to less viscous eruptions. Rhyolitic magma, which is higher in silica, is more viscous and traps gases, resulting in more explosive eruptions. The next process of volcanic eruptions would be the volcanic explosivity. This occurs through gas release and pressure buildup. Dissolved gases in magma are under high pressure. As magma rises, reduced pressure causes gas exsolution, aka bubble swarming, which increases the volume and explosivity. The role that silica content, which we previously mentioned, takes over is that silica-rich magma has a higher viscosity, making it harder for gases to escape. This leads to a buildup of pressure and highly explosive eruptions like Mount St. Helens in 1980. The third main process would be the products of the eruption itself. First, there's lava flows. Low silica lava, which is basaltic, flows easily, creating extensive fields. A prime example of this would be Hawaii's Kilauea. Then there's pyroclastic materials, which occur when explosive eruptions eject ash, pumice, and volcanic bombs rich in silica and other minerals. Finally, there's the volcanic gases. These key emissions include H2O, CO2, SO2, HCl, and HF. These gases affect the environment and climate, with SO2 forming sulfate aerosols, which are tiny particles in the atmosphere made of sulfur compounds that cool the Earth's surface. The final process would be the chemical impact on our environment and climate. Volcanic eruptions contribute to acid rain. This is when HCl and SO2 react with water in the atmosphere, forming sulfuric and hydrochloric acids. They also create aerosols and global cooling. Sulfate aerosols reflect sunlight, causing short-term cooling, as observed after Pinatubo's eruption. Finally, there's the soil and ecosystems. Ash and lava deposit enriched soils with minerals, actually benefiting our agriculture over the long term.
Now that we're done going through the chemistry and history of volcanoes, we'll move on to our experiment with a bit of information first. The elephant toothpaste experiment is a colorful demonstration of rapid chemical reactions. In the experiment, hydrogen peroxide breaks down quickly, producing oxygen gas, O2, and foam that shoots out of a container. This can be compared to volcanic eruptions, where chemical reactions and gas release also play a big role. First, let's start with the gas production. For the elephant toothpaste side of it, hydrogen peroxide breaks down into water and oxygen gas when a catalyst like potassium iodide or yeast is added. This reaction happens quickly, releasing gas that gets trapped in soap, forming foam. For volcanoes, inside of them, gases like water vapor, carbon dioxide, and sulfur dioxide are released from magma as it rises. These gases build up pressure, leading to explosive eruptions. Then we have the catalyst and speed. For elephant toothpaste, the reaction is sped up by a catalyst like potassium iodide, which makes the hydrogen peroxide break down faster. For volcanoes and magma, the speed of gas release can depend on temperature and chemical composition. Hotter magma or magma with more dissolved gases behaves like a faster reaction, leading to stronger eruptions. In elephant toothpaste, the foam represents how gas escapes from a liquid, pushing the mixture out in a burst. In volcanoes, lava, ash, and gases are ejected from a volcano when gases escape quickly from magma, creating pressure that pushes everything outward. Finally, there's the pressure and expansion. In elephant toothpaste, the rapid release of oxygen gas causes foam to expand and shoot out of the container. In volcanoes, gases escaping from magma expand as pressure drops, driving explosive eruptions.
Here's what we'll use for this experiment. The first thing we'll be using is hydrogen peroxide, the second being a catalyst like potassium iodide or yeast, the third being dish soap, and the fourth is optional, and that is food coloring for the fun visuals. And when we mix these ingredients, we get a foamy explosion, kind of like a mini volcanic eruption. Let's break it down step by step and see how each part of this experiment represents a part of a volcanic eruption. First, let's look at the gas production. In the elephant toothpaste experiment, hydrogen peroxide breaks down into water and oxygen gas when the catalyst is added. This reaction releases gas quickly, which gets trapped in the soap to form foam. Now let's think about volcanoes. Inside a volcano, gases like water vapor, carbon dioxide, and sulfur dioxide are dissolved in magma. As the magma rises, pressure decreases, and these gases escape, driving the eruption. And this is the chemical reaction for the elephant toothpaste.
In our experiment, the catalyst speeds up the reaction
making the hydrogen peroxide break down faster. Similarly, the speed of the gas released in a volcano depends on the temperature and composition of the magma. Hotter magma with more dissolved gases releases gas faster, leading to explosive eruptions. The foam in elephant toothpaste represents how gas escapes from a liquid under pressure, forcing the mixture to expand and shoot out. In a volcanic eruption, the lava, ash, and gases that burst out are driven by the same principle, gases escaping rapidly from magma as pressure builds and releases.
Here's the exciting part: pressure and expansion. In our experiment, the oxygen gas rapidly expands, pushing the foam out of the container. For volcanoes, escaping gases expand dramatically as pressure drops, powering eruptions that can send lava and ash high into the sky. By connecting this experiment to volcanic eruptions, we see how chemistry explains both small-scale and large-scale explosive events. This helps us understand not only how volcanoes work, but also how to predict and prepare for them.
Quick heads up, do not do what my friend just did, as it can be extremely dangerous and you can burn your finger.